Hey everybody, this is John. Today I'm going to show you the electronics that I built to drive the case feeder that I made for my Lee Loadmaster. So the deal with the Loadmaster is that when you raise the RAM, raise the deck, and it goes up and down, this whole assembly moves up and down. This tube will move up and down right here. So what we need to do is find some way to figure out when the moving tube is full so we can shut off the case feeder. So what I have is a sensor inside this box, an infrared emitter detector pair, and that will sense when the tube is full, and then it will shut off the case feeder. So as you can see, there's no contact switch, nothing like that, having to pierce the tube to figure out when to shut the case feeder off. Externally, all we have is an on-off switch and a red LED to show us when the case feeder is turned on, powered up, and we have a jack for the power adapter. What we have then is a bunch of wires. You know, the switch, the jack for the power, and the board. It's a perf board on some standoffs, and what we have is a couple capacitors, power regulator, and one transistor and some resistors. And then we have the motor. It's a couple wires. That's just a plug connector that I have there to disconnect the motor if I want to remove the electronics or remove the bucket or something. This is the schematic of the circuit that drives the motor of the case feeder. What we have here is a light emitting diode, resistor, the emitter detector infrared diode pair, some more resistors, an NPN transistor, another diode, and of course then the motor, and it's all driven from a 12-volt supply. Let's take a real quick look at what a resistor is, what a diode is, what a transistor is. To give you sort of a mental picture of what an electrical circuit is, think of a pump with a hose and then some type of restriction. So as you turn the pump, water will flow through the circuit, and if there's a restriction, like say the hose is pinched or something like that, pressure will build up in the hose, and the amount of pressure that you will see in the hose is a result of the size of the restriction that opposes the flow and the amount of water or whatever is trying to flow through the system. So the amount of pressure is a product of flow and restriction. Well, an electrical circuit is pretty much the same thing, except the pump, of course, doesn't produce pressure. A pump produces flow and pressure as a result. Well, a battery is the pressure. So a 10-volt battery would be a fixed 10-volt pressure, and then that pressure would try to push current through the circuit. So current is actually drawn by the load or the resistor. Now a resistor is something like, it's either a small thing like this, or it could be a coil of wire that's really poor conductivity. But in this particular case, voltage is sort of a product of current and resistance. The equation or formula for this would be V equals I times R. So if you wanted to know what the current is, and you knew what the voltage is and what the resistor is, you could easily calculate it. So say the resistor is 100 ohms, right? What you could do is V equals I times R. You would divide both sides by R to get rid of R on one side. So that would cancel the R's on this side. So therefore what you would have then is V over R equals I. So your current would equals to this. So if voltage, say R is 100 ohms, voltage is 10 volts, would be 10 volts over 100 ohms, which equals 0.1 amps. So the unit of current is amps. Voltage equals volts, and resistance equals ohms. Just keep in mind that current is drawn, and current flows from the plus of the battery to the negative of the battery through a resistor. A diode, it's a one-way valve for electricity. So it lets the current flow through this direction, but will create an open circuit and will break the circuit if electricity tries to flow in the opposite direction. So electricity flows, or the current flows through the arrow. Now, in a circuit like this then, it really wouldn't make much effect on the circuit other than there is a little bit of voltage drop across it, or you could think of like a pressure drop across a fluid circuit. But say for some reason this battery was hooked up backwards by accident. What would happen is the diode would prevent the current from flowing in the opposite direction. So it could be a safety thing or something like that. It's really good when you have like an AC circuit where the voltage source, say from the power in your wall, is like this. And you want to chop it off and you only want to get something like this. The diode can be used as a one-way valve to ignore all of the reverse polarization of the voltage. Let's say when the diode's turned on, VD, the diode voltage drop is typically about 0.7 volts. If it was an LED, a light emitting diode, this thing, when the electricity flows through it, it will actually get bright and give off light. Those diodes typically have higher voltage, like the VD across it is like maybe 1.5 volts, something like that. And the color of the diode will probably have a different VD value for the diode. So let's just take a quick example like this. When you look at the voltages around a circuit, this is your source. Everything in here all the voltages here must add up to the source. So in this particular case, since this is 1 volt, this has to be 9 volts to make up the 10 volts. That's your source. So what would be the current flow? I equals V over R, which equals 9 volts divided by 100 ohms, which equals 0.09 amps. If we put this diode in backwards, no current would flow. It would look like this. The circuit would be broken and just would not operate. Say you want the diode to be very bright. Well, the more current that you let go in the LED diode, the more current that flows, the brighter it will get. So this resistor actually adjusts the intensity of the light. Because say if you had this instead of 100 ohms, say you had 1,000 ohms, well, that would mean the current would be 0.009 amps, which is 9 milliamps. And that's probably about what you would want to have going through an LED diode, 9 or 10 milliamps. So a lot of times you'll see in my circuits, I'll have a 1 kilo ohm, 1,000 ohm resistor put with the LED. That's so you'll get around 10 milliamps, something like that. Because if it's too bright, you'll actually burn out the LED. Now, an NPN transistor is also a semiconductor device, just like the diode. To give you an idea of just how it functions, what it is, it's a current-controlled current source. Now, what in the hell is that? Okay, so you've got a base, you've got emitter, and you've got a collector. Current flows in this direction. And what happens is, you can think of it as being like a diode. So you've got some current, I'm going to call it, instead of diode current, I'm going to call it base current. And the current will flow through this direction. And you would expect, of course, current to flow through here, and what flows in must flow out. So you would have base current flowing in, base current flowing out. And of course, you'd have VD or something like 0.7 volts or something across this guy. So you'd have, like, for example, 0.7 volts across here. But you've got this other piece on it. This guy is a circuit that it will look at the current that's flowing in this direction, and it will actually also put current into this collector based on how much current is flowing here. So the current that's going to flow here is actually some gain, I'm going to call it B, times the base current that's flowing here. So not only do you get IB flowing in and flowing out, but you get IB this direction plus this other current from this guy, beta IB. So the current, or sorry, this is the emitter. So the current that flows out the emitter is actually IB1 plus beta. And this is usually around 100. Sorry, this is around 101. So what you've got then is, this is a current amplifier, you could think of it. You've got some current flowing in, and then you've got like 101 times the current that flows in flowing out. Now for the transistor to operate like this, you can't have the resistor too big that's going to be on the collector, or what happens, or you can't have the voltage on the emitter to be too high, because what happens is when the voltage across here gets too small, this thing doesn't work, and instead of being like 100, it's only going to be like, say, 10. So if you've got a transistor and you want to use it as a switch, say you've got a motor and you're going to put some current into here, you want the motor to put 100 milliamps here. Now this is going to be about 0.1 volts, and this is, say, 10 volts. That means across here you've only got 0.1 volts. This is not going to work as a very good current amplifier. The gain, it's only going to be 10. So you're going to have to put in 10 milliamps for 100 milliamps to flow here. So typically what you'll see is 5 volts here, and then you put some resistor here. You know this is going to be 0.7 volts. So then you got to have some I. I has to be like 10 milliamps to get 100 milliamps here. You've got to choose your resistor wisely, such that 5 minus 0.7, 4.3 volts across this resistor is going to give you 10 milliamps. So you need to choose resistor. V over I equals 4.3 volts over 10 milliamps equals 430 ohms. So you would have to choose a resistor like this size to get enough current to flow in here such that you're going to get the current out here. But overall, all you need to know is that the NPN transistor is just a current amplifier that can act as a switch controlled by the current you put in this direction, right? If you don't put any current in, the thing will act like a switch that's open, not functioning, and that would turn off your motor or whatever you have on the collector or emitter. Now resistors, they have color stripes on them. There's like, on this one has a brown, black, red, and then a gold. So the gold stripe on the far end, that just typically shows you what the tolerance is. Like silver stripe would be plus or minus 10% variation. Gold would be plus or minus 5% variation in piece to piece. And then you'd have like, you could have a red stripe, which would be plus or minus 2% variation in resistor to resistor if you had to pull any random one out of a bunch. So typically the way it works is, let's take a value of 1000 ohms. You typically just take the first two numbers, and this is represented by color, this is represented by color, and then these number of zeros, that's represented by color. The color scheme is like this, where each color represents a number. In our case, for 1000 ohms equals 1 kilo ohms, you'd have a brown, you'd have a black, and then 2 zeros, red. That would be your stripes. Now let's say you have a couple resistors and you put them in series like this. Well, just like the flow problem with a pump, if you've got a restriction of 100 ohms and 100 ohms, from looking at it in this direction, if you're the guy trying to push the water through this thing, it's going to look like 200 ohms. So resistors in series will add. Now, if you had two resistors in parallel, if you were trying to push water through this guy, you would see 100 ohms of resistance to flow and another ohm resistance to flow. So this actually, two resistors in parallel will make it easier to make the push the current through. So in parallel, these two guys would actually only look like 50 ohms together. So when you have two similar resistors, two identical resistors connected up in parallel like that, the overall resistance is going to equal R divided by the number in parallel. So when you don't have the exact value resistor in your kit that you want, you could take a bunch of other resistors and just put them together either in series or parallel and make up the value that you want based on this. So this is the case feeder circuit again. You've got some battery. First I put an LED, a light emitting diode here with a resistor, so when I power this thing on, the thing gets bright. I can see that the power is on. Then I have the diode pair and some resistors to set the current that flows through these guys, to set the intensity or strength of the light that flows through here. And what happens is when this light, so this guy actually acts like a little transistor. When the light flows, it's like putting current into the base of a transistor, and that will let the current flow through this guy, and then this looks like sort of like the emitter on a transistor. and the current will flow through here, will go through this resistor, create a voltage here, and then that voltage here will then put current into this direction to put current into this transistor, turn this transistor on, and then that will let current flow through the motor. Now we have diode here. What the hell is that for? And it's backwards to let the current flow this way. So actually, like we said, the diode, when it's hooked up, when you have a plus voltage here and a minus voltage here, the voltage is in reverse across the diode. So the diode actually doesn't look like anything in the circuit. It looks like it's actually gone. It's missing. It's open. But the motor draws, some current, but there's a big coil of wire inside a motor for the electromagnet. And as current flows through that guy, if you immediately try to turn off this transistor, what's going to happen is the current will want to keep flowing. Try this. Go plug your kettle in the wall and let the water start to boil, and as the current is flowing in the kettle, try unplugging that kettle from the wall. You'll see a spark jump the gap because there's a huge voltage created from the flowing current and the magnetic field in the kettle. So you get this big spark. Well, you're not going to see a spark here, but when you try to turn off this transistor, the electromagnetic field in the motor is going to try to kick back and create a huge voltage here. So the voltage here could be like maybe 500 volts or 100 volts or something. That could burn up your transistor over time. But because you get a plus 500 volts here, that's actually not going to happen because this diode will turn on and the current will actually flow through this diode to the supply up here. So the diode is actually a protection device for your transistor to help the transistor from not getting damaged when you turn off this motor. So the physical circuit, if you were to look at the transistor, you would insert it like this from looking in through the top of the transistor. The diode, when you look at a diode, its body, it's like a little cylinder. This is what one looks like. The silver mark represents the bar across the arrow tip, and these guys here are inserted the way they look. If you look closely, there is a flat edge on one of these guys. And I get the 12 volt supply to power this circuit from a voltage regulator. See my primer warning alarm video where I describe this a bit more in detail. This is the motor. One question then is, how in the hell do you hook up a motor like this when you don't have a connector? Well, what I did, I just took the motor apart, and on here I soldered wires directly to those leads on my bullet feeder and the motor I use now on the case feeder. Instead, what I do is I actually run the wire in through here, and I solder it right directly to the two terminals on the motor, and then run the wires out through here and put it all together. Also keep in mind, when you hook this up to your transistor to be powered, if you swap the direction, if you swap the two wires or swap the connections here, that's going to change the direction of your motor. So if you want the motor to turn clockwise or counterclockwise, all you have to do is swap the two wires, and that will change the direction. Well guys, that's it. It's a pretty simple circuit that you should be able to do. See my other video for the low primer warning. I go into some other things there that may help you as well. This circuit should also work for your bullet feeder. It's nice because it's so simple. But the bullet feeder, I went into some theory and detail here because the bullet feeder circuit that I use is actually pretty complicated compared to this one. And I'm not going to have time in a video to go into the details like I showed you here. That video will be coming out pretty soon. But this is a great circuit because it's so simple and so few components. The more simple it is, the less there is to go wrong. So, hope you found the video useful, and check out the other videos on the circuits there because I'm trying to not have any overlap between the videos in the information for you.